back to Notes 2.3. This is going to be on counting atoms and the mole. In your textbook, make sure you're reading the pages 322 to 342. And in your study guide, this is going to be chapters 10.1 and 10.2. All right, to start off, counting atoms in a formula, we're going to be looking at the subscripts, so make sure you write down this definition. All right, so the subscripts are the smaller numbers that appear after an element in a compound. They are in the lower right quadrant. So if we were looking at the subscript, this 2 would be a subscript here. This 2 would be a subscript here. Okay, so that's what we're talking about when we talk about subscripts. So we're going to start using the mole and molar mass. So in order to do that, we have to know how to count atoms. So our first example here, H2O. So if we take H2O, what this formula means is that there are 2 hydrogen atoms that are bonded to 1 oxygen atom. Okay, so in H2O, that's what that is. All right, and so in carbon dioxide, if we were looking at carbon dioxide, CO2, we have C, and oxygen. C, there's only 1 of those, and in oxygen, there are going to be 2, COO2. So this subscript number tells you how many of the element that it follows. All right, so in NaCl, what do we have? We have 1 sodium and we have 1 chlorine. Okay. All right, so you do NaBr2. Okay, so we have 1 sodium and 2 bromines. Okay, how about zinc chloride, ZnCl2? We have 1 zinc and 2 chlorine atoms. Okay, so now this subscript can also come after the first element like it does in H2O up here. So it doesn't matter where they're in the formula, it always talks about or refers to the element that it follows. So Na2O, sodium oxide. So there's going to be 2 sodiums and then 1 oxygen. If it doesn't have a subscript here, you're just going to assume that it's 1 because of the element symbol that's written there. All right, so now let's look at the ones where you have parentheses. This is a little bit different. So when we use parentheses, it's because this right here is what's called a polyatomic ion. So that word poly means many, or in this case, more than 1. And atomic refers to atoms. So it's many or more than 1 atom that is bonded together that acts like an ion. So it acts like a single element, an ionic element that's bonded to another element. So we have to use, if you have more than 1 of these polyatomic ions that's bonded, then we have to use parentheses around it to show that this is to be thought of as a unit. So this polyatomic ion has to be thought of as a unit. Okay, now we're going to see polyatomic ions that aren't included in parentheses, like for example, sodium hydroxide would be Na and then OH. It's 2 capital letters, so that's oxygen and hydrogen. Okay, but it's not included in parentheses. So then that would mean just 1 of those polyatomic ions, 1 oxygen and 1 hydrogen. Now, all of those that we see here do have parentheses though. So this 2 outside means that there are 2 of those ions. So what we have here is magnesium, and it's bonded with 2 OHs. So it looks like this. So if we were to count these atoms, we would have 1 magnesium. And then for the OH, we would have 2 of those. Okay, so if we split that up into its elements, we have O and H. So I'm just going to put a bracket around that. So O and H. So how many oxygens do we have? We have these 2, so that would be 2 oxygens. And then these 2 hydrogens would be 2 hydrogens. So we have 2 hydrogens here and 2 oxygens here. OH2. So this 2 acts like a multiplier for everything that's inside of that parentheses. Okay? So let's try AlNO3. So on the aluminum, of course, we just have 1 because we see that there's no subscript there, so that means 1. But we have 3 NO3s. So this NO3, if we just look at NO3, that's 3 oxygens bonded to a nitrogen, NO3. But we have 3 of those. So you can imagine it being like this. Okay, so how many N's do we have there? We have 3 N's. And how many oxygens total? There's 9. 3 for this one, 3 for this one, and 3 for this one. So this 3 here, like I said, acts as a multiplier. So this 3 goes for the N, 3 N's, and then 3 times 3 for the 9. Okay. All right. So let's look at Mg3 PO4 2. See if you can do this one. Okay, so for Mg, we're going to have 3. And for P, we're going to have 2. And for oxygen, we're going to have 8, because 2 times 4 is 8. All right, very good if you got that. And for our last one, sometimes the parentheses are on the first group, first polyatomic ion. So here we have NH42CO3. So let's see, we have N, H, C, and O. Those are the elements that are in this compound. So how many nitrogens do we have? Look closely. We have 2. Okay. How many hydrogens? 8. Very good. How many carbons? All right, so this doesn't have parentheses around it. So this 3 would not go for carbon. That only happens when you have parentheses. So the carbon, there's just going to be 1, because we're just looking at this spot here for carbon. Okay, so there's 1 carbon, and how many oxygens? 3. All right, so we're going to do some more practice on counting atoms, because that's going to be very important in what's coming up here, where we start talking about the mole. Okay, the mole is this number, 6.02 times 10 to the 23rd particles. Okay, and this was discovered by another scientist now that we're going to talk about, Amedeo Avogadro. It's actually a really, really long name, but we call Avogadro for short. Okay, and this number that he came up with is called Avogadro's number. It's named after him. And this is what we call a mole.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amedeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Fortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in the container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole, this mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is, anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
Okay, so the mole. So it's just a measurement. It's a very big number. So if we have a mole of rice, a mole of anything is 6.02 times 10 to the 23rd grains. So that's how many grains we have. A mole of hockey pucks, 6.02 times 10 to the 23rd pucks. A mole of pennies, like I referred to in the video, 6.02 times 10 to the 23rd pennies. So a mole is just a measurement in chemistry. What we're going to start doing, instead of talking AMUs, like we did in 2.2, we are not going to talk in AMUs anymore. We're going to talk in grams per mole. So when we look at carbon, for example, on the periodic table, we see that on the molar mass of carbon, on the average atomic mass of carbon, it's 12.01 grams per mole. Okay, so no more AMUs. Now this means grams per mole. So we are going to start looking at this concept called molar mass for compounds. So again, going back to the counting, if we had H2O, remember we have 2 hydrogens and 1 oxygen. So now, what is the molar mass of hydrogen? Well, if you look on your periodic table, you're going to see that it's 1.01. So we're going to multiply this by 2 to get the total mass of oxygen that's in that molecule. And we're going to take oxygen, which is 15.99. All right, so on your periodic table, instead of being 15.99, it's been rounded to an even 16. So this is an even 16. Okay? And that's the periodic table that I want you to use. The masses that are on this periodic table that we just did for our reference materials right here, please use these masses. Now, if you'll look on a different periodic table, like for example, you click periodic table here, and you bring up this, it is for oxygen, is going to say 15.99 right here, 15.999. Okay, so you see that? So 1 times 16 is 16. All right, now we're going to add these up. So that's going to be 18.02 grams per mole. That's the unit that we're going to use for this from now on. Grams per mole. So they were talking about this in the video. If you had 1 mole of water, it's going to be 18.02 grams. So that's going to be a conversion factor. 1 mole of water is equal to 18.02 grams. We're going to use that conversion factor in just a moment. Okay, so if we were going to do another example, okay, let's do NaBr2. So we have Na and Br. So how many sodiums do we have? 1. And bromine, we're going to have 2. So if we multiply this by the molar mass of sodium, the molar mass of sodium is 14.01. Okay, and you know what? I'm going to use my units because I tell you guys to use your units all the time. So I better do the same thing. So this is grams per mole. And bromine, okay, bromine is right here at 79.90 grams per mole. Okay, so we're going to multiply those out. So here we're going to get 14.01 grams per mole. And 79.90 times 2 is 159.80 grams per mole. Now we're going to add that up to get the total molar mass of NaBr2. Okay, and that's going to give us 173.81 grams per mole. Okay. Now we could do the same thing to any of these. So if you're understanding what we're doing, you can go ahead and skip ahead to the next section. But I'm going to do one more. I'm going to do one with a polyatomic ion. So let's do aluminum nitrate. So aluminum, nitrogen, and oxygen. So those are the 3 elements that we have here. So how many aluminums do I have here? 1. How many nitrogens? 3. And how many oxygens? 9. All right, so I'm going to multiply each one of these by the molar mass. So aluminum is going to be 26.98. Oops, 98. That's a parentheses there. Okay. And then nitrogen is 14.01. 14.01. And these are grams per mole. The abbreviation for mole is MOL. If you want to use that, I mean, you just drop the E. You're going to see MOL though. All right, oxygen is 16.00 grams per mole. All right, so we're going to multiply each one of these out. So 1 times 26.98 is 26.98 grams per mole. 3 times 14.01, grab my calculator. 3 times 14.01, it's going to be 42.03 grams per mole. And then 9 times 16, 144.00 grams per mole. Now remember, on all these molar masses, we're taking these out to 2 places after the decimal. Okay, so even though on my calculator it said 144, I took it 2 places after the decimal on all molar masses. All right, so now we're going to add this up. So 144.00 plus 42.03 plus 26.98. Okay, we're going to get 213.01 grams per mole. All right, so aluminum nitrate, which is the name of this one right here. Aluminum nitrate, the molar mass of aluminum nitrate is 213.01 grams per mole. So that is getting the molar mass of a compound. All right, so before we go into now the next section of this, the next section of these notes, we need to brush up on our conversion and how to do conversion factors. We studied this a few weeks ago when we first started off chemistry. So looking at this problem, suppose each bag of marbles contains 30 marbles, and each bag of marbles has a mass of 38.1 grams. So we're going to make some conversion factors out of this. So each bag, so 1 bag of marbles is equal to 30 marbles. So remember, these are conversion factors. Equalities are conversion factors. The next conversion factor that we have is 1 bag of marbles is equal to 38.1 grams. Okay, and we're going to be using those in these next set of questions. All right, so how many marbles are in 2.8 bags? Okay, so I'm going to circle my given. Remember glues? Okay, it's coming back into play. We're going to list them out, but there's only one given, so there's really no use in listing it out. We're going to underline what we're looking for. How many marbles? And then we're going to write down our equation. So remember, when we're doing a conversion, the equation is starting off with your given over 1. So I'm going to put my 2.8 bags over 1. Okay. All right, so now I'm going to do my conversion. So remember the 5 steps for a conversion. The first thing you want to do is set it up over 1. And then the steps. Step number 1, what unit do I want to get rid of? Well, the answer to that is bags. Step 2, where do I put that unit to force it to cancel? I'll put it on the bottom. Okay. Next step, what do I want to convert this to? I want to convert it to marbles. So we're going to have to look at our conversion factors and see if we have a conversion factor from bags to marbles. And we do right here, bags to marbles. So we're going to put in our conversion factor. So I'm going to convert this to marbles. So now I'm going to put numbers. So 1 goes in front of bag, 30 goes in front of marbles. Okay, the next step, cancel what you can cancel, which is we put that there so we know we could force cancel it. Then the unit that we have left is the unit we want to check to see if we're in our answer. So are we there yet? The answer is yes, because we want marbles, and the unit we have left we didn't cancel out is marbles. So we are to the unit we want. So now we're just going to do the math. So 2 times 8 times 30, 2.8 times 30. Okay, it's going to be 84. Okay, and carry over our unit, marbles, over 1 times 1 is 1. We know anything over 1 is itself. So the answer here is 84 marbles. Okay, so do you remember doing this? This was part of our unit on Foundations of Chemistry, where we learned how to do conversions. Okay, so if you understand that, if you remember that, then you can skip to the next section and skip over these other 2 examples that I'm going to do. But for those of you who are still rusty on this or feel like you want more practice, I'm going to think 2 more problems. Yep, 2 more problems. All right. So again, the same information. 1 bag of marbles is, 1 bag is equal to 30 marbles, and 1 bag is equal to 38.1 grams. So our new question is, how many marbles have a mass of 190.5 grams? Okay, so how many marbles is what we're looking for. So let's take our given, 190.5 grams. We're going to put it over 1. What unit do I want to get rid of? Grams. And what am I converting this to? Marbles. So do I have grams to marbles? I don't, but I have grams to bags. So here I'm going to put bag, because I can't go straight from grams to marbles. I don't have a conversion factor for that. So I'm going to have to go grams to bags first. All right, so let's put in some numbers. 38.1 is in front of grams, and 1 is in front of bag. Cancel what I can cancel. What unit do I have left? Bags. I'm not there yet, so I need to do another conversion factor. Start back over with the first step. So what is the first step? What unit do I want to get rid of? I want to get rid of bags. So I'm going to put it on bottom so I can force it to cancel. What unit do I want to convert to? Marbles. So I look, do I have a conversion factor going from marbles to bags? And I do. So I'm going to put marbles here. Put in my numbers. 1 bag is 30 marbles. Cancel what I can cancel. Now I have the unit that I want for my answer. Okay, so now I can stop and do the math. So 190 times 1 times 30. So 190.5 times 1 times 30. It's going to give me 5715 marbles. Okay, and multiply the bottom. 1 times 38.1 times 1 is 38.1. No unit, because all the units have been canceled out. So it's just a number. So now we need to do this. So 5715 divided by 38.1 is going to give me 150. All right. Marbles. So sig figs, we need to make sure we do sig figs here. we have 4 sig figs for our given data. So we need 4 sig figs for our answer. This is only 3. So I'm going to have to add another significant digit, which is going to be a decimal and a 0. So these are trailing zeros. So remember the rules. Trailing zeros count as significant digits if there's a decimal, and this has. So there is our answer, 150.0 marbles. All right, on our last example, what is the mass of 1 marble? Okay, so 1 marble is our given. What is the mass is what we're looking for. So I'm going to start out with 1 marble over 1. What do I want to get rid of? Marble. I'm going to put it on bottom. What am I converting it to? Mass. Well, it says here mass. What unit do we want for mass? That's grams. So do we have a conversion factor going from marbles to grams? We don't, but we do have one to bags. So we're going to have to go from marbles to bags. So 1 bag is 30 marbles. Cancel what you can cancel. Okay, so are we there yet? No, because we have bags and we want grams. We want a mass. All right, so all over again, what do we want to get rid of? Bags. What do you want to convert bags to? Now we can go from bags to grams. So we have a conversion for that. So 1 bag is 38.1 grams. Cancel what you can cancel. We're left with grams. That's what we want for our answer. So we don't need any more of that line. We can erase that. Now we can do our math. 1 times 1 times 38.1 is 38.1 grams. Pull our unit over. No unit on the bottom. 1 times 30 times 1 is 30. So 38.1 divided by 30 is 1.27 grams. How many sig figs do we need for this? 1 sig fig. So we're going to look at this. So 1 significant digit here. There's the 1 significant digit. So does the 2 round the 1? It does not. So our answer for this is 1 gram. Okay. Had this been, what is the mass of 1.0 marbles? If they had actually had a number in there, then this would be 1.3 because we'd have 2 sig figs. And if they did this, 1.00 marbles, then it would be 1.27 grams. So depending on how the number of sig figs that you have depends on how accurate the answer is going to be. All right. So you may have seen this picture in your book, and this is what's called the mole map. And this is the diagram that helps us convert between particles, volume, and mass. The mole map that I like to use to give you looks like this. So go ahead and write this down. Okay. So let's look at the mole map they give you in the book. It's basically the same thing, only it's flipped upside down. So if I take the mole map they give you in the book and I flip it upside down, representative particles here, representative particles there, grams, mass over here, and then volume and volume. So it's the same thing, it's just flipped upside down. Okay, but this is the one that we use in this class. All right, so how does this work? This is a map that lets us convert between mass to moles to representative particles. And representative particles can be molecules, atoms, or formula units. Those are 3 words that you're going to see in problems. Okay, so representative particles could mean any one of these three terms. And it lets us convert from mass to moles to volume. We can go from volume, anywhere there's an arrow, that means that you can go to that unit. We can go from volume, which remember is liters, or anything with a prefix like milliliters, centiliters, to moles. To representative particles, we can go from volume to moles to mass using this map. Okay, and these right here are the conversion factors that you use to get between those. All right, so let's keep this handy and let's talk about some problems now. All right, so how many moles of sodium chloride are in 10 grams? Okay, so there's our given. How many moles of sodium chloride are in 10 grams? So we're going to start with our given, 10.0 grams. And we want to go to moles. So let's look back at our mole map. So how do we do that? Well, it's just like any other map. When you're using a map, you look at where you're starting and where you want to end up. Okay. And then on any other map, it shows you the route to get there. So if we're starting with a mass, like 10 grams, and we want to get 2 moles, that's our destination. We're starting here and we want to get to here. So there's our route. Well, how do we get there? We get there by using the molar mass. Okay, so this is going to be our conversion factor, the molar mass. All right, so now we're going to have to back up and think about molar mass. Well, remember, molar mass is you take each one of these elements, you find out how many atoms make up that compound, and then you add it together, and that's called molar mass. So in order to get from grams to moles, we have to calculate the molar mass of NaCl. So we have Na, we have one of those. In chlorine, we have one. So what is the mass of sodium? Sodium is here, it's 22.99. So 22.99, and that's grams per mole. Okay. Chlorine is right here, 35.45. So 35.45 grams per mole. So now we multiply these. It's just multiply by 1. And then we add them up. So if I take my calculator and I do 22.99 plus 35, oops, let's try that again. I pressed the wrong number. 35.45, I'm going to get 58.44 grams per mole. So what does this mean? That means that 1 mole of sodium chloride is equal to 58.44 grams. This is a conversion factor. Remember, conversion factors are equalities, something that's equal. So this is going to be our conversion factor that we're going to use in this problem. So once we get our conversion factors all set up, then we can start our problem. Okay, question number 1, what unit do I want to get rid of? I want to get rid of grams. What do I want to convert it to? I want to convert it to moles. Now, on our mole map, we see that we can do that. We can go from grams, which is a mass, straight to moles. So that's just one step. So here's where we bring in our conversion factor right here. Okay, so what goes in front of mole? 1. What goes in front of grams? 58.44. Cancel what you can cancel. Are we there yet? Yes, we are. So I don't need any more of this line. I can erase that. Now I can just do my math. 10 times 1 is 10. Bring over your unit. Over 1 times 58.44 is 58.44. The grams has been canceled, so we don't have a unit there. So 10 divided by 58.44. Okay, this is going to be, on my calculator, 1.711156,742 times 10 to the negative 1, or on your calculator, if it's not set up for scientific notation, it's going to be 0.1711156,742. Okay, these two numbers are exactly the same. My calculator gives it to me in scientific notation. Your calculator gave it to you in standard notation because it's not that small of a number. All right, so we're almost done. How many significant digits are in our data? This is 3 significant digits, or sig figs. When you see this abbreviation when I write stuff like on the answer sheets, SF means sig figs, significant figures or significant digits. There's 3 here. These trailing zeros count as significant digits because there's a decimal there. So my answer can only have 3 significant digits. So here's 1, 2, and 3. So I'm going to look at this 1 to see if it rounds. That 1 does not round. So if you're going to write this in scientific notation, it would be 1.71 times 10 to the negative 1 mole is our unit that we have left. Or if you're not writing it in scientific notation, it's going to be 0.171 moles. That's the answer. Okay, so how many moles of sodium chloride are in 10 grams? The answer is 0.171 moles. Okay, so pretty simple. So let's try another one. All right, this is how many grams are in 7.9 moles of aluminum nitrate. So 7.9 moles, there's our given. I'll go ahead and put it over 1. And this is of aluminum nitrate. So we're going to need to start using this as part of our unit. Okay, so 7.9 moles of aluminum nitrate. And we'll put that over 1. And it's asking how many grams. So let's go back to our mole map. So it gives us moles is where we're starting, and grams is where we're ending. So moles is where we're starting, grams is where we're ending. So we have one step. We can go straight from moles to grams. We're going to use to get there the molar mass. So I have to calculate the molar mass of aluminum nitrate. So we have aluminum, nitrogen, and oxygen here. So how many aluminums do we have? 1. How many nitrogens do we have? 3. And how many oxygens do we have? 9. Okay, so I'm going to have to multiply by the molar mass of each one of these elements. So aluminum is 26.98. And remember, these are all grams per mole. Okay, nitrogen is 14.01. You can check me on the periodic table. And oxygen is 16.00. Many of you ask me, do we have to memorize the periodic table? No, but because you use this information so much, you're just going to naturally remember it like I did. All right, so we need to multiply each one of these. So 1 times 26.98 is 26.98. 3 times 14.01 is 42.03. And then 9 times 16 is 144.00. Okay, now we need to add these up. We're going to get 213.01 grams per mole. So that means 1 mole of aluminum nitrate is equal to 213.01 grams. All right, so we have our conversion factor set up. We can go ahead and start this problem. What do I want to get rid of? Moles. What do I convert it to? Grams. So our conversion factor is 1 mole is equal to 213.01 grams of aluminum nitrate. Okay, so we can go ahead and, put these down here. All right, so moles of aluminum nitrate cancel moles of aluminum nitrate. Are we there yet? We are, because we wanted grams. So grams of aluminum nitrate. And we just do our math. So 7.9 times 213.01 is 1,000. Let's see. 1, 2, 3, 1682.779 over 1 times 1 is 1. Okay. So we have 1,682.779 is our numerical answer. Oops, 9, not G. All right, so how many sig figs do we want? 2. All right, here's 1, here's 2. Now, here we have a problem. Remember, if you have numbers on the left side of a decimal, you can't just drop them off. Do you remember what we have to do? We're going to use this 8 to round. So the 8 does round that to a 7. So we have 1 7. Do you know what to do at these two places? The 10th place and the 1's place? We have to have placeholder zeros. And then what's on this side of the decimal we can drop off. So our answer is 1,700 using our significant digits. So how many grams are in 7.9 moles? 1,700 grams of aluminum nitrate. All right. So we're going to go a little bit faster here. So how many molecules are in 5.9 grams of sodium chloride? So, oops, that wasn't a very good circle. We're going to circle our given. Underline what we're looking for. Then we're going to go to our mole map. It says how many grams are in this many molecules. Okay, I'm sorry, how many molecules are in this many grams? So we're going from grams to molecules. So we're going to start here at grams and we're going to go to molecules. Now remember, I said representative particles could mean molecules. That's vocabulary that it's using here. So we cannot get there in one step. This is going to go 2 steps. So we're going to have to start with mass and get to moles. We're going to have to go from moles to representative particles. We're going to use the molar mass and Avogadro's number to get there. All right, So start with our given, 5.9 grams of sodium chloride over 1. Okay. We know we need the molar mass of sodium chloride, so let's just go ahead and calculate it. Okay. We have 1 sodium, 1 chlorine. Sodium is 23.99. I'm sorry, 22.99. I'm glad I looked at that. 22.99. And chlorine is 35.45. I'm going to look at that just to show you. 35.45. Okay, so that's times 1. So we just have to add these up. 22.99 plus 35.45. We're going to get 58.44 is the molar mass of sodium chloride. Okay, and this is grams per mole. All right. And the other conversion factor that we're going to need is 6.02 times 10 to the 23rd particles per mole. Okay, so particles per mole. Remember, 1 mole, Avogadro said 1 mole is equal to 6.02 times 10 to the 23rd atoms. So we can use atoms, molecules, or formula units. So particles per mole, particles, right here, particles per mole. So I don't want that to confuse you. All right, so 6.02 times 10 to the 23rd particles is equal to 1 mole. All right, so we have our conversion factors set up and we can start this problem. So what do we want to get rid of? Grams of NaCl. What are we going to convert it to first? Look, grams to what? Moles. So this actually tells you what to put on top here. Moles. All right, so let's look at our conversion factors. Which one are we going to use? Well, let's look at our mole map. It tells us we're going to use molar mass. So here's the molar mass, so 58.44 grams per 1 mole. So 1 mole is 58.44 grams. Okay, cancel what I can cancel. And this is moles of NaCl. Grams cancels out, so now we're in moles. Back up to step 1. What do we want to get rid of? Moles of NaCl. And what are we converting it to? Molecules of NaCl. Okay, 1 mole of NaCl is 6.02 times 10 to the 23rd molecules. I was going to put a line there, but we don't need another conversion factor because when we cancel what we can cancel, moles cancels moles, we see that we're in molecules of NaCl. So I can stop and do the math. So our unit is going to be molecules of NaCl. We have no unit on the bottom. So we have 5.9 times 1 times 6.02 times 10 to the 23rd. Make sure you put this in your calculator correctly. You use the EE button. Okay, so this is going to be equal to, oops, that's 3.5518 times 10 to the 24th. Okay, so see, we have to use scientific notation here. Divided by 1 times 58.44 times 1 is 58.44. Okay. So we're just going to divide that by 58.44. We're going to get 6.077686516 times 10 to the 22nd power. All right, so we need to count our sig figs. How many sig figs do we need? We have 2 sig figs in our given data, so this can only be 2 sig figs. 1, 2. So we look at the 7 for rounding purposes. All of this doesn't matter. 7 does round to 0 to a 1. So this is going to be 6.1 times 10 to the 22nd molecules for our answer. So that's how many molecules are in 5.9 grams of sodium chloride. All right, so the only one we haven't done an example for is volume for liters. So this one is going to be, this last example is going to be for that. So we're going to go from molecules of nitrous oxide or nitrogen oxide to liters. How many liters? All right, so we're going from molecules to liters. So if we look at our mole map, we're going to start here with representative particles. We're going to have to go to moles. And then we're going to go down to volume, which is in liters. We're going to use Avogadro's number here. And then here, we're going to use 22.4 liters is equal to 1 mole. That's what that 22.4 is. So that's going to be our conversion factor there. So here it's 1 mole is equal to 6.02 times 10 to the 23rd. Okay. So look back at your mole map. My mole map is too far backwards for me to flip back there, so I just rewrote it. But this is the path, this is the route that we're going to have to take. So let's start with our given 5.4 times 10 to the 24th molecules of nitrogen oxide over 1. Okay, what do we want to get rid of? We want to get rid of molecules. And I'm just going to shorten it. I'm going to leave NO off. We're going to convert it to moles because that's our first stop, particles to moles. So 1 mole is 6.02 times 10 to the 23rd molecules. That's Avogadro's number. Cancel what you can cancel, molecules. So now we're in moles. What do I want to get rid of? Moles. So I'm going to set it up to cancel. I'm going to go from moles to volume, which is liters. See, it's asking liters. Okay. So 1 mole is equal to 22.4 liters. Cancel what I can cancel. So I'm left with liters. That's what I want for my answer. So I'm going to do the math. So 5.4 times 10 to the 24th power times 22.4 is equal to 1.2096 times 10 to the 26th over 1 times 6.02 times 10 to the 23rd times 1 is 6.02 times 10 to the 23rd. Okay, so now I'm going to do that math. And that's going to give me, well, I'm going to write, I got scientific notation on my calculator, so I'm going to write it down. And then I'll write down what you got because it's in standard notation. 2326 times 10 to the 2nd power. Okay, and what you got on your calculator is 200.94 0.302326. All right. So sometimes this is why it's better to have your calculator set up in scientific notation, because we have 2 sig figs that we need for our answer. So here's 1, here's 2. I need this 0 to tell me if I round, and 0 does not round, so all of these numbers I can drop off. So the answer is 2.0 times 10 to the second power. Now, if you're in standard notation, this is 2 sig figs, so 1, 2. So we look at here to see if we round. The 0 does not round, so we have 200 point. None of this matters, but we only need 2 sig figs. If we put a decimal place there, that makes that 3 sig figs. Okay? So let's not use the decimal. If we don't use the decimal, we have trailing zeros here. That makes this 1 sig fig, because these zeros aren't going to count. So the only way to possibly write this with 2 sig figs is by writing it in scientific notation. Well, since my calculator is already in scientific notation, I have the answer. But if your calculator is in standard notation, you're going to have to convert this over yourself to scientific notation. So in order to get it scientific notation, we move the decimal place until it's after the first number. So it's 2.0093 blah, blah, blah times 10 to the, how many times did we move it? Second power. Well, that's what I got for my calculator already. So by having my calculator set up in scientific notation, I can avoid this extra step. But you do whatever you want to do. The answer is 2.0 times 10 to the second power liters. Okay? All right, so that concludes the 2.3 video. We're going to do more problems in class for bell work, and then you're going to have problems that you're going to do on your classwork that I'm going to give you. If you need help, make sure that you ask for help. Make sure that you like this video, hit that like button, slap it right across the face, hit the bell so you know when I put up videos, and we'll see you in class.